So let's see what are some usual indicators of Six Sigma project team performance. So here are some examples. Interdependency between the team members. So this is typically associated with how well people work together in order to accomplish a task. And also how we can piggyback on each other's specialized skills in order to complete a task or activity faster and better. Now we're going to discuss about some key team performance indicators associated with Six Sigma projects. So there are some key indicators related with team performance. And if you take a look at a series of Six Sigma projects, well, we'll see that there are two types of teams, those that are performing well and those that are not performing well. So these are some examples of this type of indicators. First of all, interdependency. Interdependency has to do with how well the team members are working together, as well as how each team member piggybacks on other team members' skills, knowledge, and experience in order to expedite, for example, a process and complete it faster than usual. The next indicator is the team mechanics. Referring to team mechanics, is associated with routines within a team, like a Six Sigma project team. For example, one routine can be the daily stand-ups. So first thing in the morning, the project team is gathering together in front of a board that is used in order to indicate the progress of the project. And each team member has to answer three very specific questions. The first one is, what did I do yesterday? In other words, what type of tasks or activities associated with the projects I completed yesterday? Which tasks and activities I'm planning to complete today? And finally, if I have any obstacles in successful completion of the tasks and activities that I have been assigned. So this is an example of team mechanics, daily stand-ups. These are also known as morning prayers or morning head rules. Communication. When we refer to communication within the context of a team, first we have to look at how team members communicate with each other. And this has a formal element, which means that repeated communication activities are typically included in the communication plan of a project, and also informal communication between team members, which is something very common, especially in lean Six Sigma projects. Conflict resolution. So this is about resolving issues arising between team members during a project in a constructive but also consistent and realistic way. And finally, support. Do we have supports from top management, and is the support visible? And also, is the top management walking the talk? In other words, are they participating in project-related events? Are they demonstrating commitments by allocating resources like people, money, and everything else that the team needs in order to successfully complete the project. Now let's make the contrasting between low-performing Six Sigma teams and high-performing Six Sigma teams. And these are some of the typical characteristics of each of these two types. Poorly performing teams, first of all, they have a tendency when team members are acting independently without communicating, for example, with the project manager and other team members when they go and they perform a task. Lack of defined rules. So in each project, it is very typical that at the very beginning, the team establishes some rules, and these rules should be followed consistently throughout the duration of the project. For example, we should all participate in the daily stand-ups. First thing in the morning, every day, same place, same people, no exceptions. Another one could be we always volunteer in order to help other team members to complete a task if we see that they're struggling. We try to finish tasks and activities on time in a systematic and a consistent way, etc. Struggle communicating with each other. Now, this is a typical indicator of a poorly performing team. This means that there's no cohesion between the team members, and the chemistry within the team is not about right. Failing to resolve conflict by following rules that the team has established, and this is referring to the team mechanics we mentioned earlier. And finally, lack of visible support from the top management. For example, for providing the required resources when they're needed, and also by participating in project activities and showing performance and visible supports from the top. Some characteristics of high-performing Six Sigma teams. Well, first of all, there's a lot of collaboration between the team members. And of course, this also means that team members are communicating effectively amongst each other. Well-defined team mechanics, which are the rules set up by the team that everybody follows and adheres to. Conflict resolution process. So we deal with conflict if and when it arises. And we do it in a systematic way, and we do it in a realistic way. And finally, high-performing Six Sigma teams, they have all the resources they need in order to complete the tasks and activities associated with the project when these resources are required. So, another important topic is about how we choose Six Sigma team members. And to answer this question, we have to think about the different types of Six Sigma projects. And for each type of project, we need to make sure that we have cross-functional participation with subject matter experts from different parts of the organization. And also, we have the team leader, we have the facilitator, and some of the other common key roles and responsibilities that we already mentioned. Now, some of the key attributes. Listening. So, when we talk about Six Sigma team members, we should be thinking about good listeners, people that listen carefully when another team member, for example, is expressing their views, instead of just focusing on what they're going to say or the question they're going to ask, after the team member speaking, has finished. Critical thinking. Critical thinking means that we can distinguish between what is priority task and activity and what is not, and also the distinction between fact and opinion. Six Sigma is a fact-based and data-driven methodology. So making sure that we consider information in an objective way is very, very important and fundamental. And finally, team players. This means that they collaborate well with the other team members, they work well with others, and they can also act independently if and when this is appropriate. Another characteristic is willing to join in meetings and perform some routine tasks. Earlier in our course, we discussed about the power equation or the transfer equation. Y equals a function of x, which means that an output in a process depends on an input plus the procedure that we use in order to transform the inputs into an output. So, very relevant topic is the term correlation and the term causation. So when we're talking about correlation, in Six Sigma projects, it is very typical in order to try to determine if there is a relationship between two variables, for example, an x, which is an input, and a y, which is an output. So what we do is we change the inputs and we observe what is happening in the process output. Causation is a slightly different term because we try to establish if there is a causative relationship between two events. In other words, if one event triggers the other event to happen. We have two examples. The first one is a laptop that runs out of battery, and the second is a smartphone or an iPhone that lacks the appropriate RAM, random access memory. So in the case of the laptop, when it runs out of battery, this causes the computer to shut down. So that's one example of causation. But also, running out of battery may cause a video player that is not going to work. As a next step, we try to establish if there is a correlation between the two causes. Computer shutting down and video player will not work. In the other example, lack of RAM causes a phone to freeze, which means it renders it unusable. And also, lack of RAM may cause text messaging that is not going to work. Again, the next step is to try to establish if there is a correlation, if there is a relationship between a phone freezing and text messaging that is not going to work. So this is the distinction between correlation and causation. Now, correlation, as the word indicates, means interrelationship, usually between two variables, an x and a y, an input and an output. So in statistical terms, this is used in order to signify the extent of the relationship between two variables. So correlation measures the strength of the relationship between two variables. And it can be positive or it can be negative. Now, referring to the figure with the title Correlation, we can see that we can have a strong positive correlation. This means that by changing one variable, the other variable responds in the similar way. For example, if the height of a person increases, then the shoe size also increases. That's a strong positive correlation. We may have a weak positive correlation between two variables, or we may have a strong negative correlation. Negative correlation means that when we make a change in one variable, for example, if we increase it, then the response is that the other variable decreases. So it goes the opposite way. That's why when we see an upward trend, we're talking about a positive correlation, and a downward trend is a negative correlation. Now, the two variables can be positively correlation when they move together in the same direction, like the first example of strong positive correlation. Or they are negatively correlated if they move in opposite directions, just like in the strong negative correlation. We may also have some cases when there is no correlation at all between two variables, an x and a y. Now, speaking about correlation, we see on the graphs that typically we have a straight line indicating correlation, and you have data points or plots that are closer or further away, from that line, which is known as line of best fit in statistics. So we must differentiate between correlation and causation, because ideally we should be changing only one independent variable, for example, an x, an input, at a time, and observe the effect on the dependent variable, the y. An example. Let's say that we want to test a new drug and see how it affects the blood pressure of a patient. This means that we can administer it, for example, at a low dosage, like 10 milligram, and see what kind of effect it has on the blood pressure of the patient. Then we can increase it to 20 milligrams and also measure what kind of effect it has on the blood pressure. So, when we find that changing the independent variable, the x, makes a difference in the output, the dependent variable, but changing another input does not make a difference, then you may have found what we call a causative effect. An input that has a significant effect on the output. I mentioned earlier about inputs indicated as uppercase X's, which are critical process inputs, and also critical process outputs indicated by uppercase Y's. Now, when we compare these two terms, correlation and causation, it does not necessarily mean that because we have an indication of correlation between two variables, necessarily changes in one variable actually cause changes in the other variable. In other words, correlation does not prove also causation. In statistics, and we're going to explain later in our course, we're looking at linear correlation. In other words, if we compare different values of x and y's, then the so-called line of best fit is a straight line. Because usually, when the line is not straight, this means that there is no correlation between the two variables. Let's have a look at an example. So, in one figure, we try to see if there's a correlation between a medical condition, which is autism, and organic food sales. Now, if you think logically and ask yourself the question, is there a correlation between these two variables, autism and organic food sales? Well, the answer should be logically there's no correlation between them. So if we take a look at the graph, we see that the line of best fit, or regression line, as we also call it, is not a straight line. It's a curved line. So in a case like this, we say that we have, no correlation between the two variables. To summarize again, correlation between two factors, an x and a y, does not necessarily imply or prove that changes in one cause the changes in others. So how can we apply this causal theory in the context of a DMAIC project? In the define phase, we have to look at our process outputs and distinguish what is the issue associated with the output. For example, it may be a lot of variation in the process, and this may cause a product or a service to be outside of the customer requirements, the customer specification limits. This can be an example of an issue. In the measure phase, we measure the inputs and we measure the outputs. For example, we take measurements of product parts at each stage of the production process, and we check material strength, material density, and composition. In the analyze phase, we have to prioritize the outputs. In other words, we have to distinguish between the critical outputs and all the other outputs. The critical outputs are very important to the customer. They represent the voice of the customer, and as we're going to learn, they are known as CTQs, critical to quality requirements. And these are associated with characteristics of the process output. So you can ask the question, which of the process outputs are most contributing to the issue? You can test whether the issues in your highest priority sub-process are caused by the inputs or the procedure. The input is an X, the procedure is the function, the F. For example, vary material qualities in some tests and the manufacturing sub-process and procedure in others. In the improve phase, this is when we implement some strategies in order to improve your inputs or procedures for a high priority sub-process. And during the control phase, we put measures in place to monitor the future inputs and the procedure. And usually, if you remember, we standardize the process during the control phase. We document the standardized process, and every process participant is expected to follow the process as it has been improved. So there must be commonality among all the process participants, and this is going to result in minimal variation between how different people do the same task several times. Now we're going to summarize some key points associated with the problem-solving strategy, which is the equation y is a function of x. So the first one, if you have a problem with a process output, this may have two potential sources, your inputs and your procedure for transforming the inputs into an output. So these two potential sources are not mutually exclusive. Most processes are quite complex, so in order to negotiate them effectively, we may have to break them down into a sequence of sub-processes or process steps, as we call them. We have to prioritize the problem outputs. In other words, we have to focus on the critical outputs first before we start thinking to address the less critical process outputs. Remember, critical process outputs are represented with the uppercase letter Y, and these are associated with customer requirements that are very important for the customer. So when we're dealing with problems in a sub-process, this can be replicated and enlarged as its output moves through subsequent sub-processes. In other words, if you have, for example, 3 sub-processes, A, B, and C, sub-process A has an input and an output. Now, the output of sub-process A becomes input in sub-process B, which produces also an output. And the output of sub-process B becomes an input in sub-process C, which also produces an output. So it is just like a chain of interdependent subtasks or process steps. Now, these are important figures because they explain in slightly different ways how the Six Sigma DAMAIC methodology really works. So we have one figure that is associated with inputs. So we can see that as we move between the different phases of DAMAIC, from define to measure, from measure to analyze, from analyze to improve, and from improve into control, then we keep reducing the X's, the causes that contributes, to the issue in the process output. For example, during the define phase of DAMAIC, we have to consider all possible inputs in a process, all the X's, both uppercase X's and lowercase X's. Moving to the measure phase, this can be reduced to the so-called first hit list. So we may go, for example, from more than 30 process inputs into 10 to 15 process inputs. And gradually, as we move through the DAMAIC stages, we see that during the control phase, we typically have determined that there is a small number of critical X's. And by monitoring these critical X's, then we have the desirable effects in the process output. Also, this is an interesting figure illustrating how Six Sigma DAMAIC works. And you may notice that there is color coding associated with the different phases of DAMAIC and the transformation that is taking place between the DAMAIC stages. So if we take a look at the right part of the figure, we see that at the beginning of a project, we recognize that we have a business problem that must be resolved. This is recognizing, and this is associated with the so-called problem statement. So during the define phase, we set up the projects, we set up the project control documentation, we identify the key stakeholders, etc. Now, as we move from define to measure and from measure to analyze, during the measure phase, we try to establish what is the current state of the process under investigation and also determine how capable is the process in order to meet customer requirements and customer specifications. And this is when we identify areas of potential process waste, as we call it. During the analyze phase, we analyze the data that we collected during the measure phase, and we try to find the root causes associated with each form of process waste. So we create a list of validated root causes. During the improve phase, we brainstorm using as a basis the list of validated root causes in order to identify solutions that either will eliminate these root causes or at least reduce them to an acceptable level. And during the improve phase, this is the first time that we make actual process changes. And once we have made all the changes that we decided that should be piloted and implemented, then we have a very good understanding of the process. So during the control phase, we monitor the improved process to make sure that it's stable, it meets customer requirements, and the changes that we made had the anticipated effects. And finally, at the end of the control phase, we formally close the project, and this is when the benefits realization period begins. Now, we see that at the center of the DAMAIC methodology, we have the voice of the customer representing customer needs, wants, requirements, specifications, etc. And we also have the voice of the process, which indicates how capable is the process under investigation to satisfy the requirements of the customer. On the left side of this figure, we see the transformation as the project goes through its stages. So we start with a practical problem, we convert it into a statistical problem, we find a statistical solution, and we convert the statistical solution into a practical solution. And finally, the practical solution is associated with the process changes to improve the process. We set up a control plan based on which we will monitor the improved process. And finally, we look at results, the benefits deriving from the process. So there's a correlation between the right side and the left side of this particular image, and the color coding will help you establish the relationship.
you.